Welcome back. We're going to look at Module 2.5 now. This is systems of equations and inequalities as opposed to individual equations and inequalities. Now this is, I think, one of the more challenging parts of the CLEP. It requires us to be able to both plot pictures efficiently and also do calculations very efficiently. So we'll start with linear systems, then we'll work our way to linear inequalities, and then also mixes of linear and even quadratic equations, which can get a little bit hairy, but I think we'll be able to do it. So let's start with a classical formulation of this problem. The idea is I have two lines. So here in my picture, I have plotted in MATLAB one line in red, which you can see in red, and then another line in blue. And the goal is to find their point of intersection. So when are these two lines hitting each other? Right, so another way of saying this is that if I write y equals m1x plus b1, and another line y equals m2x plus b2, find where they meet, but I want it in terms of m1, m2, b1, and b2. So basically, given the formulas for the lines, can I compute, at what x value they're hitting and at what y value they're hitting? Okay, so another way of writing this is to have this this brace here, this bar, that tells me I want to solve these equations simultaneously. So I want these both to be satisfied at the same point. So I think that the easiest thing to do is what I'm calling the classical solution method. So we essentially say, well, I have one expression for y, I have another expression for y, so I can just set these equal. So I can say m1 x1 plus b1 should be equal to m2 x plus b2. This will help me determine the x value. I'll solve this as an algebraic equation in x. And then once I have the x value, I'll plug back into either line and get the y value. And this will tell me the point in the plane at which the lines are intersecting. So let's look at an example. So I want to plot, because it's always good to plot if you can. It kind of keeps you on the right track. So we'll say plot and solve algebraically the following. Y equals 2x plus 1 and y equals minus x minus 1. So let's start with the plot. And of course, this is mainly just a tool for us to kind of help us learn and build intuition, and then also to make sure we're on the right track. Okay, so let's start with this one. The y-intercept is 1 and the slope is 2. So something like this, I'll call this 1. And then 2 has a slope is here. The slope is minus 1. So the picture is something like this. So my intersection is somewhere there. So I have some intuition about where it is, but I don't have exact formula for it. So what I do is I'll set the two lines equal to each other, solve for the x value, and then plug back in for the y value. So let's do that. So I'll say 2x plus 1 equals minus x minus 1. This tells me that 3x is equal to minus 2. So x is equal to negative 2/3. So that tells me in my little picture what the value on the x-axis is. Now I'll go back and say that y is equal to 2x plus 1. And I'll plug in x equals minus 2/3 to get y equals 2 times minus 2/3 plus 1. Minus 4/3 plus 1, so this is minus 1/3. So the point of intersection is 2/3 minus 1/3. That's this point that I'm about to highlight in green right there. Those are the exact coordinates for it. So I think this illustrates, A, what the method should be to get them algebraically, to get exact formulas for x and y, but also sort of what the virtue of plotting is here, is it gives us sort of like a sanity check, right? We knew that, okay, it should be small negative x value, small negative y value, and that was confirmed by our algebraic computations. This can sort of be a way of telling if you're way off, if you forgot a negative sign in your computation somewhere. Okay, so let's look at another example. So let's plot and solve another system of equations. 3y minus 4 equals 6x plus 1. And 2x equals y minus 7. So we'll put these into slope-intercept form. So plotting is easier. In slope-intercept form. So let's do that. So 3y minus 4 equals 6x plus 1. This is the same as saying y is equal to 2x plus 5/3, and 2x equals y minus 7 is the same as saying y equals 2x plus 7. So my rough sketch is something like whoops, this no, okay, 1, 2, 3, 4, 5, 6, something like that, and then 2x plus 3, something like this. So the point that I want to make here is that these are parallel lines. Right? They have the same slopes, too. I mean, right? They have different y-intercepts, but that doesn't matter. That just means I intersect the y-axis in different places. But the key point is that these are parallel. So I have lines with the same slope. Well, essentially the main point of parallel lines is that they never intersect. Okay? They're always staying the same distance away from each other. Right? So in particular, there's no way for these two lines to hit each other. So just from the plot, I know that there are no solutions to this system of equations. Right? So I'll write this as parallel lines don't intersect. So this is like saying that there are no solutions to my inequality. So another case of when plotting can be very, very convenient for us. It gives us some sort of geometric information about the lines, which we can then use to infer, okay, roughly where do the lines intersect? And in our case, we see that they're parallel, so they don't intersect at all.